vectors for simple things that are in like the x, y, and z planes. But if it's a three-dimensional vector that has an arbitrary orientation, then the only way you could really do it well is by calculating the cross product, excuse me, for my verb. But remember, when you do the right-hand rule for the cross product, your thumb is just telling you the orientation of the axis. And it's telling you whether that force would cause a tendency to rotate counterclockwise or to rotate clockwise about the axis. Magnitude of torque is given as the magnitude of each of these vectors times the sine of the reference angle between them. Today, we're going to learn about net torque. You guys already know about net forces, that if the mass of a system remains constant, but the net force is the product of the system's mass times its acceleration. But we could also apply Newton's laws for forces for torques as well. If you have a net torque, then the sum of the torques about some axis, and actually I'll say about any axis, the sum of the torques is equal to I alpha. So for forces, we have mass. For torques, we have this symbol I. We're going to define this to be rotational inertia. Rotational inertia is the tendency for objects to resist changes to its rotation. Just like mass is the tendency of an object to resist changes in motion, rotational inertia is the tendency of an object to resist changes of rotation. So what we're about to do is we're about to derive a result for rotational inertia. So how we're going to do that is, let's say we have an arbitrarily shaped mass, and let's say we're going to rotate this mass about this axis. So I'll call this axis O. So this whole mass is going to be a rigid body, rigid meaning everything moves with the same angular velocity. So actually, that's a definition for rigid body you may want to write down. A rigid body is a body in which all its parts move with the same angular velocity. A rigid body is a body in which all of its parts move with the same angular velocity. A rigid body is a body which moves, where all of its parts move with the same angular velocity. So for example, if I move my torso, and pretend I don't have any legs, if I move my torso, my arms and my torso can be considered a rigid body because my arms and my torso each sweep out the same angle in the same amount of time. So they're all moving with the same angular velocity. Versus if I just have spaghetti noodles for arms, you know, my hands are moving with higher angular velocity than further. So this would not be a rigid body. This is a rigid body. Angular rotational inertia is defined for any body. But I'm going to just start off with a rigid body, and what we're going to do is this applies for any body, whether it's rigid or not rigid. So what we're going to do is we're going to break up this rigid body into a bunch of tiny pieces of mass. So each one of these little pieces correspond to a tiny bit of mass. So I'll call this piece 1, I'll call this piece 2, I'll call this piece 3, piece 4, piece 5. Now, what we're going to do is let's find the total kinetic energy. So that's demonstrating a rigid body on the screen. Bunch of particles. So if all of these spheres represented particles that made up the rigid body, then all of those particles are moving with the same angular velocity. So let's derive an expression for the total kinetic energy of a rigid body rotating about a stationary axis. So here's our axis of rotation. Our rigid body can be described of all of these different pieces. And what I'm going to remember is that the kinetic energy is defined as 1/2 mass times speed squared. So if we want to find the total kinetic energy, we're going to have to sum all of the masses. And this is going to be just the sum of 1/2 mass of the ith body, speed of the ith body squared. So I'll just write that out here. So let's see if we can come up with an expression for the kinetic energy of each body. And the thing we know is each body is rotating with the same angular velocity, omega. So to do this, let's look at this first particle. So this first particle is a distance r1 from the axis of rotation, and it has mass 1 unit of mass. So we will say mass 1, and if we look at this, if this were rotating in a circle, then this first particle is rotating in a circle. And we know a relationship between speed and angular velocity, right? Speed is equal to the radius times the angular speed. So for this first particle, I'm going to replace this with, actually, let's do it like this. I'll just write it like mi ri omega I quantity squared. So if we look at this then, let's sum up all the pieces. 1/2 mass of the first particle, radius of the first particle, angular speed of the first particle squared. So that's the first particle. Let's sum that to the second particle. So here is radius 2. I'll go ahead and do radius 3, radius 4, so on and so forth. So if we start summing all of the kinetic energy terms, mass 2, r2, omega 2 squared, plus mass 3, r3, omega 3 squared, plus on and on. Yes, sir?
It's just the w squared?
It's omega, not W. So what's your question?
Oh, it's in parentheses with the r radius.
Is it
Oh,
r squared?
sorry.
Oh,
Okay, those are all squared. Thanks. Okay, so if we look at this, all of these have the same angular velocity. So I am going to factor out that angular velocity. Because since it's a rigid body, they're all moving with the same angular velocity. And let's do something else. let's make all of these tiny bits of mass have the same value. So mass 1, so we'll say let mass 1 equal mass 2 equal. So they're all identical pieces of mass. That's just spread out. Yes, sir?
It says right there, particles of various masses.
Yep. Various masses, but I'm saying, I'm going, and what we're going to do is we're going to start making this smaller and smaller looking under a microscope. Okay? So I'm going to make them identical now, but I'm starting off with them being different. Okay? I'm taking it to a limit. So I'm taking it just like in calculus, how you take a line and you break it up into tiny little pieces, and each piece you say are identical pieces. That's essentially where I'm going with it. So if we do that, then this becomes 1/2 1/2, and actually we'll say it's delta m. Nope, lost my train of thought. Sorry, let me back up a little bit. Actually, what I will say, I will back up here because I do think it's better at this point. I do think it's better to consider them different. So I will back up. Instead of saying they're all the same, I'm just going to say let mass 1 be a tiny bit of mass. Let mass 2 be a tiny bit of mass. Let mass 3 be a tiny bit of mass. So we're dealing with tiny bits of mass. So when I do that, then we have a tiny bit of mass 1, r1 squared, plus a tiny bit of mass 2, r2 squared plus ... So watch what happens when we take these tiny bits of mass. So this then becomes the sum of I equals 1 to n of 1/2 omega squared, and notice what's left inside. Delta m I r I squared. And this is representing the total kinetic energy. And notice this is kinetic energy based off of rotation. So, what do you think happens when I evaluate the limit as n goes to infinity of this? Can I write this more simply? This is something you've seen before in Math 3A and 3B. Yes, as an integral. The sum of a bunch of tiny little pieces. Here we have a sum of a bunch of tiny little masses. And we have an infinite number of tiny little masses. And this is where those masses all become identical, because we have an infinite number of tiny little masses. So an infinite number of tiny little masses, this becomes the integral.
W squared.
I'm sorry?
Is W squared still in there?
Yeah. Thank you. This becomes the integral of a bunch of tiny little masses. So I'm going to replace this with an r squared dm. dm is our integration variable. Here's our r squared. So each quantity varies as a function of distance. So this is basically the integration over the mass. And we're going to call this something. this quantity right here, we're going to use the variable capital I. And we are defining capital I to be rotational inertia. Yes?
So just to clarify, the delta M is just like smaller pieces of mass?
Infinitely small because we have an infinite number of them.
Okay.
Yep. So we now have a definition for rotational inertia. The rotational inertia for a solid body of matter is given by the product, really, of mass times the distribution of that mass. Because notice, this R term means where these masses are placed matter. A mass placed here matters. A mass placed here matters. The shape of this object matters. The tendency of this object to rotate about this axis is dependent on the distribution of matter about that axis. If you change how that object looks, or if you change its shape, you're going to change its ability to change rotation about a particular axis. And I want you to notice something. When we broke this up into very tiny pieces of mass, see all of these identical terms? We are going to say that I, for a point particle, and I'll just put it on that board over there. When we divided that mass up into a bunch of tiny little point particles, so they're points, no size, just mass, we could say that the rotational inertia of a point particle is equal to mass times r squared. And remember, r is defined as the distance the point mass is from the rotation axis. Now, the reason why I wanted to derive that